So in my first video, I kind of went over like what Laplace transforms were and how we can take a function. The two we did was e to the lambda t, right, and t to the power of n. How we can take the Laplace transforms of those and get them into a function in terms of s. So we go from the t domain to the s domain, right? And what you found was that the Laplace transform is really just an integral, right? We're putting these functions in an integral, right? So we'll have an integral with respect to t, so it's dt. It's an improper integral, so it's from 0 to 100. Sometimes we need integration by parts. We typically do. In this exponential example, we didn't, but we just evaluated the limits, and what we got was that for e to the lambda t, right, our solution here was 1 over s minus lambda, and our solution here was n factorial over, it was s to the n plus 1, I believe. Okay, so we kind of derive those. And I think, like, honestly, when you do like a mechanical engineering course or an electric circuits course or just a straight up differential equations course, you're going to have a table of all these transforms. But I think it's good to see like where they come from, because you're probably already kind of confused with like how we're getting these formulas after we derive them. So just imagine seeing these on a piece of paper with having no idea like how we even get them, right? It's pretty crazy stuff. So without knowing how we can actually apply them yet, this stuff, I agree, it is confusing. Okay, so I just keep saying you got to keep trusting me, okay? Because eventually probably in the next, I'd say 3 videos after that, we're going to get into differential equations and you're going to see why these are so important, okay? When we're solving differential equations. So let's take a Laplace transform, kind of keep building our table of the cosine of bt. Okay, so this is just a cosine function, right? B determines our period. So the period, remember, is 2 pi over b. Doesn't matter a whole lot, but if we were to graph it, right, if b was big, the period would be small, so it would be really skinny like this, right? Doesn't matter, but that's just what b is, right? So if it was cosine of 2t, right, a pretty common function, that means b would be 2. So when we solve this thing, we're going to have a b in there most likely. We're going to plug in a 2 there if that was our function. Okay, so we remember now that this is just an integral, right? That's really what the Laplace transform is. It's an integral from 0 to 100 of, well, if we just plug in e to the negative st, and then we get cosine bt dt, right? Okay, what we're going to do now is we're going to have to integrate by parts. So the only time we really don't integrate by parts is if it's an exponential, because we can add these exponents, but any other time, like if it's an exponential times a trig function or times a polynomial, right, that's really our only option, because it's an integral of 2 things that are multiplying that we can't simplify. Okay, so for this one, we're going to go u equals, u, honestly, for integration by parts, when we're deriving these, is always going to be e to the negative st, because it's super easy to take the derivative of that. So du is negative, remember it's du here. Let's do actually dv first, and I'll go back to the du in a sec. I'll show you why. So dv is cosine bt. Okay, and let me just see here. Negative st. Just kind of reading over what I have here. Yeah, so if we have cosine bt there, this would be dt, and this would be 1 over b sine bt. I'm just making sure this is the right way to set it up. I'm just looking it over here. So the derivative of e to the negative st, right, if we're taking the integral, it would be negative 1 over s times this. But if it's the derivative, it's just going to be e to the negative st times the derivative of negative st. So with the integral, it's times 1 over the derivative, but this time it's just times the derivative. So it's going to be negative s e to the negative st. Okay, so when we plug all this in, right, it's going to be the integral of e to the negative st, so that's our u, right? And then cosine bt dt is our dv. So we can see how this kind of sets up with integration by parts. And remember, integration by parts says this integral right here is equal to uv minus the integral of v du. So remember, this integral is from 0 to infinity. So our u, right, was e to the negative st. Okay, and then our v was 1 over b sine bt. Okay, so times 1 over b sine bt. That's just, we found this v just using u substitution, right? We could, I'm not going to drive it, but you guys could do it yourself, right? I'm sure that's a calculation that you could make there. And then this is going to be evaluated from infinity to 0, and then minus the integral from 0 to infinity. I'll try and squeeze it in here. 1 over b sine bt times negative s to the e to the negative s, or s times e to the negative st dt. I'm not going to have room to write that. So let's evaluate this limit first, and then I'll rewrite the other stuff. Okay, so if we plugged in infinity for t, right, what this really is 1 over b e to the negative infinity sine infinity, right? That's when we plug in infinity for t. Okay, and that's going to be minus 1 over b e to the 0 sine 0. Okay, so let's simplify this here. We get 1 over b, that's just a number, right? B is a constant. E to the negative infinity, that's just going to be 0. So this part right here is 0. Okay, and let's evaluate this. 1 over b e to the 0, right, that's just 1 times sine 0, which is 0. So that 0 is going to dominate. It's going to be 0 minus 0. So just like in the other one, the 0 is kind of not a factor of this anymore. So I'm going to erase all of this because it's just equal to 0. And the nice thing about Laplace transforms is that this happens a lot. So for our functions f of t, when we do integration by parts, this uv term typically will just go away. Okay, it's just typically going to go away. So we're left with, right, minus the integral from 0 to infinity, okay, of 1 over b, this is 1 over b sine bt. Right, I'm just plugging in what we know. So v was that, and then du is negative s to the negative, or sorry, yeah, negative s times e to the negative st. And there's a dt on that because we're integrating with respect to time. And anytime we're doing this, we always want to pull out the constants. Okay, so this is a function of t, this integrand right here. So anything that's not a t or connected to a t, we're going to try and pull out here. So this 1 over b is a constant. Same with this s. Everything else is kind of stuck where it is because sine bt isn't a constant, e to the negative st isn't. So notice how this negative and negative can make a positive because everything's multiplying. So it's going to be positive now, s over b, because that's like 1 over b times s, times the integral from 0 to infinity of e to the negative st sine bt dt. Okay, and at this point, what we're going to notice is kind of like in the last video where I showed you when we took the Laplace transform of t to the n, right? We got some term out in front, and then I'll just write I don't know. I'll just write alpha for something here times the Laplace transform of t to the n minus 1. Right? In this case, it's a similar situation, right? We had 0 for our limit of uv, so that just went away, and we were left with this integral, and we had some kind of term out front here, some constant. So it's some constant times, right here is the Laplace transform of sine bt. Okay, so we took the Laplace transform of cosine, and we got a term out front, times the Laplace transform of sine bt. Okay, so that's kind of interesting, right? So now we can kind of generalize this here. If we, So if we took the Laplace transform of cosine bt, right, this would be s over b, like we just found, times the integral from 0 to infinity of e to the negative st sine bt dt. Okay, and if we kind of kept doing this, right, if we redid this process, I'll kind of do it with you, honestly. I'll do s over b, because that's what's in front, and then we got times, we would just do integration by parts on this guy right here. So it would be negative 1 over b, I'll just kind of write it out, e to the negative infinity. I'm not going to write out all the steps, but I'm going to write out kind of how we get it. Right, minus 1 over b, e to the 0 goes 0, so this is really our uv evaluated from 0 to infinity. And then, of course, we have minus sb times the integral from 0 to infinity of e to the negative st cos bt dt. So notice how this turns back into cos. It's going to keep flipping back and forth because when we integrate or differentiate cosine, it just flips back and forth from sine and cosine. The only difference is a negative there. So this part right here, or not this part, right, is going to be 0. This part's going to be 0 if we evaluated that. And what we're left with is it's going to be negative s over b, right, times this integral right here. And if we simplified that, we still have s over b on the outside. And then we just have times s over b on the inside. Or sorry, 1 over b, not s over b. 1 over b. Or sorry, this isn't 0, my bad. 1 over b times e to the 0 is just 1, times cosine of 0 is 1. So this is actually 1 over b. So this is 1 over b here. So this is minus 1. Yeah, this is going to be minus 1 over b and then minus s over b. That's my bad. So this is going to be 1 over b minus s over b. Okay. And then we're going to have times the Laplace transform of cosine bt. Okay. And we don't need a plus c here because it's like we're no longer in the t domain, right? We're in the s domain. So saying like plus c doesn't really make sense. And also it's because this is a definite integral. If it was an indefinite, maybe we'd think about it. But in this case, no. So now we've kind of gotten to the s domain, but now we just have cosine of bt again. So to simplify for like what the Laplace transform of cosine bt actually is, right, we just kind of simplify all this junk out in front. Okay, so the Laplace transform of cosine bt, right, if we simplify this, we'd get s over b squared minus s squared over s minus s squared over b squared, and then that would be times the Laplace transform of cosine bt, right, because we started with the Laplace transform of cosine bt, we kind of did it recursively twice, and this is what we ended up with, but we still have a cosine bt term here. So like an integration by parts, sometimes when you integrate an integrand multiple times, you see it on both sides. And when you see that happen, you can think of it as an equation, not just like you evaluating an integral. Okay, so if we move this to the right side, right, and we factor everything out, we're going to get the Laplace transform of cosine bt. That's our common factor, times 1 plus s squared over b squared. That equals s over b squared. Okay, so, and now, obviously, right, just to solve for the Laplace transform here, we divide both sides by 1 plus s squared over b squared. And clearly this will simplify because the other side is pretty similar. So we get the Laplace transform of cosine bt. Once you simplify it, it's s over s squared plus b squared. Okay, and we're just going to say s is greater than 0. Okay, that's the only condition there. So the Laplace transform of cosine is some variable s over s squared plus b squared, where b is a constant. Okay. Now the next one I'm going to do is, well, remember we found the Laplace transform of cosine bt was equal to s over b times the sine, or the Laplace transform of sine bt. Okay, and now that we know what the Laplace transform of cosine bt is, we can plug that in there. So s over s squared plus b squared equals s over b times the Laplace transform of sine bt, right? And then when we divide both sides by s over b, that's just multiplying by b over s. And what we'll notice is that this is going to be b over s squared plus b squared. So it's super similar to what we had before, right? But this is the Laplace transform of sine bt. Okay, and same thing here, s is greater than 0. So we've essentially just solved for the Laplace transform of sine bt and cosine bt. So if you think about it, right, we're just building our table of Laplace transforms. We've done exponentials, e to the lambda t. We've done polynomials, t to the n, right? We've done sine bt, cos bt. All we're doing right now is really just building our table of Laplace transforms. That's really all we're doing. And I'm just showing you how we can actually derive the formulas rather than just giving them to you. Because I think if I just gave them to you, like, it wouldn't really hold a lot of meaning. But if we derive them, you're going to know, like, when we actually use them, how we got them, right? And why they're so important, okay? So I hope this is helpful, and I'll be talking soon about different properties of the Laplace transforms, probably in my next video. So thanks for listening.